Now, if you think integration's great and you think trig identities are great, then I have got the topic for you. We're going to integrate with trig identities. So I'm going to state all of the things that we're going to be using right at the start. On the right hand side there, you've got the trig identities that are going to be relevant today. And these are all ones that you've got to learn. None of these are specifically written in the book, although you can derive them from some of the things that are. You've also got the standard trigonometric integrations on the right hand side as well. These ones here are given in the formula book, and cos and sine you've obviously got to know yourself. So let's go straight to it. And there's like 8 or so trig identity integrations that come up again and again, so we're just going to go through them. First one here is tan squared. Now we mentioned this I think in the chain rule episode as one that we can't do, but we can do it using a trig identity. Specifically, we can use this top trig identity here, tan squared plus 1 equals sec squared, which we could rearrange to saying, well, if tan squared plus 1 equals sec squared, then I can rearrange that and say tan squared on its own is equal to sec squared minus 1. So we could replace that in there. We could say that we're actually integrating sec squared x minus 1 dx. And why is that useful? Well, because sec squared is something that integrates, and 1 is something that integrates. Sec squared, according to this, goes to tan x, and what minus 1 obviously just goes to x. And don't forget the plus c. So yeah, that's the idea. We swap it from something we can't integrate into something we can, and then we integrate it. What about cot squared 4x? Well, we're going to be using the second of our trig identities. We know that cot squared plus 1, and I'm actually going to write in the arguments this time, equals cosec squared. And you can always change like x in any of those identities to anything you like. So in this case, I'm changing them both to 4x. The plus 1 obviously won't change. And then I can rearrange this to cot squared of 4x is cosec squared of 4x minus 1, and that looks like something we can work with. So I want to integrate cosec squared minus 1 all dx, and what would cosec squared go to? Well, we know that cosec squared goes to minus cot, but this is that whole f of ax plus b thing from last time, where we have to put a 1 over a at the front of it. So this is going to go to 1 over 4 of minus cot 4x, and then minus 1 is going to integrate up to x, and then there's a plus c. So we might tidy that up and say we've got minus a quarter, lots of cot 4x minus x plus c. But yeah, that's it. What about sine squared and cos squared? Now you might be tempted to go to the identity that's been there since the start of A-level, that's sine squared plus cos squared equals 1. And there's a reason we don't use this. It enables us to change sine squared to cos squared, and it enables us to change cos squared to sine squared, but none of those are things that we can actually integrate. So we're actually going to use one of the double angle formulas instead. We're going to hone in on these two cos 2x formulas specifically. And let me show you what I mean. This is a really useful standard result to know. If I take the top one of those, which is that cos 2x equals 1 minus 2 sine squared x, we can rearrange this. I can swap essentially the cos 2x and the 2 sine squared x. Essentially I'm adding 2 sine squared and subtracting cos 2x from both sides. Then I can divide by 2, so sine squared x is a half 1 minus cos 2x, and then that is a form that I would actually like to have. Cos 2x is something I can integrate because it's just this integral down here. Cos squared can't, cos can. That almost sounds like it means something. So let's do that. We want to integrate a half of 1 minus cos 2x. What do you do with a half? Well, with any integral, you can take out a constant and put it at the front of the integral and come back to it later. So we'll do that. And then we just need to integrate this. So we've got our half. 1 is going to integrate to x. Cos 2x, well, minus cos to be precise, integrates up to minus sine. But again, it's that f of ax plus b thing. We need to divide by a, so it's going to be a half sine 2x plus c. And that's it. You could expand the bracket, but I don't feel like that makes it any nicer. And the same thing's going to apply to this second integral here. We're going to use cos 2x again, but we're going to use the version that has a cos squared in it. So according to this, cos 2x is 2 cos squared x minus 1. But that doesn't quite match what we want. We want a cos squared of 3x minus 1. So we're going to have to change all of the x's into 3x minus 1's. So 2 cos squared 3x minus 1. And then, because that was x, this is 2x, so it's going to double on the other side. We'll have cos of 6x minus 2 is equal to that. Now we still need to get cos squared on its own, so let's rearrange. We'll add 1 to the other side. So we'll have cos of 6x minus 2 plus 1 is 2 cos squared of 3x minus 1. And then we'll halve. So we've got a half of cos 6x minus 2 plus 1 is cos squared of 3x minus 1. And that's a substitution that we can use. So we're going to swap in that this is, let's take the half out straight away, the integral of cos of 6x minus 2 plus 1 dx. So what does cos go up to? Well, cos goes up to sine. The argument's going to stay the same, but again, f of ax plus b, we need to divide by that a, we need to divide by that 6. And then 1 is going to go up to x. And then there's a plus c. And again, you could expand it out. You could get yourself to, I think, a 12th sine of 6x minus 2 plus a half x plus c, but I don't feel like that helps anyone. Make sure you do know this 3-step process here. It comes up a lot with trig integrals. And so by process of elimination, this page must be on the sine 2x identity, and you're right, it is. Let's use that. So in its simplest form, if we see 2 sine x cos x, we can swap that out for a sine 2x. So the first example here should be fairly straightforward. What would we do with that? Well, sine x integrates up to minus cos x, or minus cos 2x, but then we've still got that f of ax plus b here, so we need to divide by 2. And then don't forget the plus c. But what about something like the one down here? Sine of 4x minus 3 times cos of 4x minus 3. This is a case where we have to consider the argument. So it's true to say that sine 2x is equal to 2 sine x cos x. What we could do is we could swap all of those x's for 4x minus 3's to make it sort of match up to what we've got here. So the right hand side would be 8x minus 6, because there's 2 of them, and the right hand side would be 4x minus 3 as our arguments. Now it still doesn't look quite like what we've got. We need to take out that factor of 2, so divide across, and we can say a half of sine 8x minus 6 is sine of 4x minus 3 times cos of 4x minus 3. Now that is what we can use. So we'll sub that in. We say we're actually wanting to integrate, and let's take the half out straight away. Sine of 8x minus 6. And so we know sine goes up to minus cos. We know that the argument is going to stay 8x minus 6. And we know, and we've also got this half at the front. And we know we're going to divide by a as well. So this is going to be minus an 8th cos of 8x minus 6. Now I might tidy this up a little bit. I might say that I've got overall here minus a 16th cos of 8x minus 6. And don't forget the plus c. Cool. A few more to go. So try to pick a few which aren't maybe quite so one step. First one we've got here is sec squared plus tan squared. Sec x plus tan x all squared. And we're going to expand this essentially. So let's do that. because there's no identity that just works for sec x plus tan x. So we'd have a sec squared out of there, we'd have plus 2 sec x tan x, and we'd have a plus tan squared x, all dx. Now which ones of those can we already integrate? Well, sec squared is one that we know how to do. Sec tan is one that we already need to do, or know how to do, so the only one that might be a problem is tan squared. So what do we do with tan squared? Well, with tan squared, we use this formula. We know that tan squared of x plus 1 is sec squared, so we can say that tan squared is equal to sec squared minus 1, and we can sub that in. So, tidying that up a little bit, we'll end up with integral of sec squared plus 2 sec x tan x plus another sec squared minus 1, and you might well then just combine your sec squareds together and say this is overall the integral of 2 sec squared x plus 2 sec x tan x minus 1. What would that give us? Well, sec squared is going to go up to tan, so we're going to have 2 tan x from our 2 sec squared, and then our 2 sec x tan x is going to go to 2 sec x, again using our sec x tan x integral, and then 1 on its own is just going to go up to minus x, and then we should have a plus c, and that's it. What about the next one? Sine squared cos squared. Now remember what we said about sine squared and cos squared? We tend not to want to put them together, we tend to want to use that cos 2x formula. This is a situation where you can sort of get around that. You might be able to do something with cos 2x, but this is quite similar to the sine 2x formula. That's got a sine cos next to each other, and this has got sine cos next to each other. So let's show you how we can use that. Well, it's true to say that sine 2x is equal to 2 sine x cos x. What we're going to do is square both sides. So it's true to say that sine squared of 2x is equal to 4, got to square the number, sine squared x cos squared x. Okay? What can we do with that? Well, we want it to look like sine squared cos x, so we need to obviously divide by 4. And there's our starting substitution. We can swap out what we've got there for a quarter, let's put that outside, of sine squared 2x. But sine squared 2x is still not something that we can integrate. We still need to do some rearranging with that, and now we're going to use the cos 2x formula. So we know that cos 2x is equal to 1 minus 2 sine squared x, but we want sine squared 2x in this, so we're going to have to double the arguments. We're going to have to say cos 4x is equal to 1 minus 2 sine squared of 2x, and we're going to have to rearrange that again. So let's do this in a few fewer steps. We swap the sine squared and the cos, and then we divide by 2. And now we finally got it into a form that we can integrate. So we can say, we can take out the half as well. So we've actually got here an eighth lot of the integral of 1 minus cos 4x. Oof, that was rough. So what would that give you? Well, 1 goes up to x, cos goes up to sine, that's minus cos, so it goes up to minus sine, but also we need to divide by the a. So there you go, the full integral. You could expand it if you wanted. You could say we've got an 8th x minus a 32th sine 4x and then plus c. But you can see how all these identities and all the reverse chain rule that we started out looking at last time, they all sort of start combining together, and this is what makes integration difficult. Okay, one last challenge. Sine to the power of 4x. Now if this was differentiation, we'd be laughing, we could use chain rule. There's no real equivalent here, we're going to have to use identities to break this down. So I'm going to start by using this one, that cos 2x is 1 minus 2 sine squared x, and I'm going to rearrange that, and we've done this a few times, so let's go straight to it. We can say that sine squared x is equal to a half lots of 1 minus cos 2x. Okay, that's not quite what we want though. We want sine to the 4x, so we're actually going to square both sides here, and to the power of 2 is going to square up to the power of 4. Half is going to square up to a quarter, and then we're going to need to expand this bracket. So if we were to do 1 minus cos 2x squared, what would that give us? It would give us a quarter, and then we'd have 1 minus 2 cos 2x plus cos squared 2x, and that is the substitution that we're going to make here. So we want to integrate, and let's take our quarter outside. 1 minus 2 cos 2x plus cos squared 2x. Is that all integratable? Well, 1, yeah. Cos is something that we've integrated since the beginning. But cos squared isn't. So we're going to have to do something with that. We're going to have to, again, use this version of the cos 2x formula. So again, we've rearranged this a couple of times now, so let's jump ahead a little bit. We know that cos squared of x is equal to 1 plus cos 2x, half of that. But we don't have cos squared of x, we've got cos squared of 2x, so we're going to have to increase our arguments here. So cos squared of 2x is a half lots of 1 plus cos of 4x. And that's the substitution we're going to make. So, what have we got here? We've got a quarter, lots of 1 minus 2 cos 2x, plus a half, lots of 1 plus cos 4x dx. Lovely. Now, something you can do with integrals is you can sort of split them up into separate bits. So you might do that, but you'd have to remember that you're timesing the whole thing by a quarter at the end of all this. So how would that look? We would have, overall, we've got a quarter times the integral of 1 minus a quarter times the integral of 2 cos 2x, and then we'd have plus an eighth if we were to put that quarter and that half together. Lots of 1 plus cos 4x. Does that make life any easier? Well, maybe I'll take this quarter and this 2, and I put them together and make that into just a half. Alright, that's about as nice as we can make it. Let's do it. So, integrating this, 1 would integrate up to x. Then cos 2x would integrate up to sine 2x, but we'd need to divide by the half. Then 1 would integrate up to x, and cos 4x, well, cos would still integrate up to sine 4x, but we'd need to divide by the 4, and then we'd have a plus c at the end. So we do one last tidy through this. We've got a quarter of x minus a quarter of sine 2x plus an eighth of x, and you might collect those last two terms together to give yourself, I think, 3/8 of x. But I'm probably not gonna, because I'm just about out of space here. Plus a 32th of sine 4x plus c. Job done. So yeah, trig identities are new. A beautiful pairing.